Alright, in this lecture, we will discuss the nature of number calculations in a computer. Because computers represent all information, including numbers, with just two symbols, and because these symbols are stored in fixed-length registers, we need to understand how these two constraints affect the way that computers perform numeric calculations. Computers store all information in codes that consist of words that all have the same number of bits. Consequently, the number of unique words in a code is determined by the number of bits. For example, if the computer uses 32 bits per word, it can represent over 4 billion unique numbers in the code. Consequently, when we perform calculations with the computer, we need to account for the size of the words and their limitations for representing numbers. Before we dive into binary addition, let's review how we add numbers in decimal or base 10 representation. When we add two decimal numbers, we add one column at a time and move from right to left. When the sum of the column is greater than or equal to the base, we carry a value into the next column with greater weight. So we carry a 10 from the ones place into the tens place. When the sum of the column is less than the base, we carry a 0 into the next column with greater weight. So in this column, we carry a 1 digit of weight 1000 to the next column, and in this column, we carry a 1 digit of weight 10,000 to the next column. Now let's return to computer addition. If we use a 4-bit architecture, and we use standard unsigned binary representation, the architecture can represent 16 unique numbers per register, 0 to 15. Let's look at a 4-bit architecture and discuss how to perform addition within these architectural constraints. Let's add 4 plus 6. The sum of 0 plus 0 is less than 2, so we carry 0 to the next column. The sum of 0 plus 1 is less than 2, so we again carry a 0 to the next column. When we add 1 plus 1, the sum is greater than or equal to the base of 2, so we carry 1 bit of weight 8 to the column with weight 8. If you're wondering why I'm carrying the 0 bits, you have to remember that we are designing systems for a computer. When we implement any operation with a computer, we want to make the operation algorithmic. In other words, we want the computer to perform the same series of operations repeatedly, over and over and over again. So, by explicitly carrying the zeros, we have made the operation algorithmic. Let's further examine this algorithm by adding 3 plus 3. Now we have 1 plus 1, which is 2, so we carry a 1 to the higher weighted bit of the next position. And then we have 3 ones added together, so we carry the higher weighted bit to the next position. And then we have 1 plus 0 plus 0, which is 1, and then we carry the higher weighted bit of 0 to the next position. Finally, we have 3 zeros, which sum to 0, and we again carry a 0 to a higher position. Notice that this 0 would need to be stored in a 5th bit. But since we don't have a 5th bit of storage, this 0 will not be stored within the computer. Because we cannot store this 5th bit in a 4-bit architecture, we need to make sure that our 4-bit additions do not result in sums that are greater than 15. For example, we cannot add 10 plus 12 within this architecture because we cannot represent 22 with just 4-bit binary representation. When we store the sum of this addition operation, we will erroneously store 6.